Hi, AP Chemsters. This is Mrs. Vanderwall bringing you 9.4 Blankwalle. This is all about ionic bonding. We're going to do some with Lewis symbols, and then we'll spend the rest of the time doing lattice energy. So you probably want your calculator handy when we get to do that. Let's go back and see what we just did in 9.3. We're talking about how these ionic bonds form. If we go back and look, is it up here, I think? If electrons are transferred, this is what we're talking about. Metal and non-metal, an ionic bond is formed. Metals will do what? Will give to the non-metal, so the non-metal has a filled shell. All right, we've already covered C. We're not going to cover it now. Okay, so let's kind of go back and look at this. So ionic bonding, what happens? The metals are going to lose and the non-metals are going to gain. So what I'd like to do first is go back and talk about valence. Let me do this real fast. Valence electrons. How many valence electrons does potassium have? Do you remember? Well, look at your periodic table. It's in the first column. It has 1 valence electrons. How many valence electrons does chlorine have? You remember that? It's in group 17. It's going to have 7. Hopefully that rings a bell. So now what? All right, what happens when K and Cl bond? Well, let's look at it here. What do the metals do? We just talked about it. Metals are going to give, come here, its electrons to chlorine. All right, and what just happened when I did that? Well, when potassium gave an electron away, help, I lost an electron. I'm positive, it becomes a K+. And what did chlorine do? Chlorine gained it. So you'd put little brackets around it. And why do you put brackets around it? Because chlorine gained those electrons. So you put brackets to show that chlorine has all, potassium has none. This is like a wall. You can't share electrons through a wall, can you? This is clearly not sharing, all right? This is clearly ionic. Potassium gave, chlorine gained, all right, accepted it. And notice we also put the charge here around chlorine. Okay, so what's happening to electrons? Well, let's look at the electron configurations of these. Can you please go and do the electron configuration, the full one, please, of potassium? Go ahead and take a second and do that. Hopefully you got this. And while you're at it, do chlorine for me. Go ahead and do the electron configuration of chlorine. All right, and hopefully you get this too. So what has happened, all right? So if I'm going to do K+, all right? So here is the 4s electron. Do you recognize it? I put it in red again. What is this electron, this outermost electron going to do? It's going to give it here to the chlorine. So this is my K+. What do you notice is totally gone now? The 4s shell is totally eliminated. It's been given away to chloride. And what does that mean for the ionic radius? Oh, the ionic radius just got smaller, didn't it? You now have more protons and electrons. Those electrons are going to squeeze in, all right, because there's going to be more attraction. You have a greater effective nuclear charge. Does that ring a bell? And so because it's gone, that 4s electron is totally gone. Well, where did it go to? Well, it went to the chloride right here, all right? So I'm going to overlap it. So now how many electrons total is in the 3p shell, all right? Hopefully you figured out it is 6. So this is the electron configuration of chloride, all right? So what has happened now? We have actually a lower effective nuclear charge. We now have more electrons than protons. The attraction has gone down. The radius is bigger because we now have a filled shell, okay? So let's look at problem number 3. Use the Lewis symbols to predict the formula and the compounds that form between sodium and sulfur, okay? So go ahead and start off, and will you please draw the sodium ion, the sodium Lewis structure and the sulfur Lewis structure. Go ahead and pause this and draw that if you need to. All right, is this what you got? All right, so what are we going to do? Well, just like we did before, all right, we're going to do this, all right, and what do you notice? Sodium is now lost its outer shell. That's good news. But what about sulfur? Sulfur isn't so happy about this, is it? So what's going to happen here? I need what? I need another sodium. Oops. So I have another sodium now, and what can I do? I can now move this over here. I guess I'll stick it right there. And now what? I needed 2 sodiums for 1 sulfur. So how do I predict that formula? Well, I have 2 sodiums, right, and 1 sulfur. But what do I do there? I have to put brackets around it, and it has a -2 charge, doesn't it? So what would be my predicted formula? Ready? Well, if I need 2 sodiums and 1 sulfur, what's the formula? Na2S. Okay, that wasn't too bad, was it? Let's go to the next page. I think there's another one. All right, so here's my calcium, here's my chloride. So watch what happens. All right, I'm going to donate the one here, and chlorine is hunky-dory. But what about calcium? Calcium isn't so hot there, is it? So I need a whole nother chlorine here, so I can donate this one over here. And now each chlorine is okay, calcium is fine. So what have I created? I've created a calcium 2+, and I have 2 chloride minuses. So what's my formula? I have 1 calcium and 2 chlorines. So what about the next one? I have magnesium and nitrogen, all right? So let's check this one out. All right, so if you haven't done so already, there is the Lewis structures for magnesium and nitrogen, a valence of 2, valence of 5. So, all right, let's do this. I'm going to put 1 here and 1 here. And row, Mrs. Vanderwalle, we have a little problem here. Yeah, I see that nitrogen isn't done yet. I need another magnesium. All right, so I'm going to put 1 here. And, oh no, what does this mean? Mrs. Vanderwalle, I need another nitrogen. Okay, so I'm going to put 1 over here. Oh no, this nitrogen isn't ready yet. What does that mean? I think I need another magnesium. All right, so I'm going to do this. And I'm going to do this. All right. Hey, I think I figured it out. All the magnesiums got their electrons taken away. The nitrogens have their octets full. So what am I left with? I have 3 magnesium 2+ ions because they gave away their 2 electrons. I have how many nitrogens here? It looks like I have 2. And now what? What's the actual formula? It is that. All right. So that is like part 1 for section 9.4. The rest of 9.4 is all about the lattice energy. And this is the rest of the story. So this and section 9 I think it's 10, the very last thing, we're going to skip some and then go to 9:10, are the last 2 pieces of the enthalpy story. Okay, so lattice energy is the formation of an ionic compound from its constituent elements. They're going to be exothermic, all right? So I'm going to have, well, let me go down here. Sodium metal solid plus a half a chlorine gas makes NaCl. And the delta H was -411 kilojoules per mole. Oh, that was from chapter 6. You may or may not remember that, okay? It's like a heat of formation, that kind of a thing. And so what would we do? We would look this up in the back of the book, and these 2 are going to be zeros, right? We could find delta H. But it says, but wait, I thought sodium chloride was created by the attraction of a sodium ion and a chloride ion, not sodium element and half a chlorine compound, but it is, all right? So how does this work, okay? Well, the lattice energy, by definition, is the energy associated with the formation of the crystalline lattice of alternate cations, it should be and anions, to form gaseous ions, all right? Or from, not for, from. It is from gaseous ions. So look at this picture. I think it's a cool picture. Look at these gaseous ions are coming together. Zoom, all right? It's like, you know, these things are coming together towards a black hole or something, all right? Zoom, this attraction is bringing them together. So this is how they're flying through the air, zoom, to attract each other, and boom. This is what you get, all right? Gaseous ions collide or coalesce. I said collide, all right? Heat is emitted. What does that mean? Exothermic. So for this, the equation for what I'm trying to show you is here's my sodium ion gas plus my chloride ion gas makes, boom, solid sodium chloride. And that delta H from this reaction is your what's called the lattice energy. All right, so how does this reaction really occur? Do you think these ions are gases just floating around and stop this in air ready to collide? No, it probably is not. So how does this reaction really occur? All right, it's in a series of steps. So guess what? You got to use Hess's law again. That's awesome. Let's go to the next page. Sorry about that. I didn't realize I didn't stop this. So you probably saw me scrolling up and down. I apologize. So I was trying to figure out how can I make this picture show up on this screen, but hopefully you're looking at it yourself, okay, on your own paper, because this is just too big for me to get on the screen all at once. So I'm going to scroll down here. And this is sodium chloride or sodium solid metal plus a half a chlorine gas. And my goal is to get down here to sodium chloride. But it's not that simple, all right? So what's going to happen? This is a series of steps. I'm going to first of all make this sodium solid into this sodium gas, all right? Well, what's that called when you go directly from a solid to a gas? That's your sublimation, isn't it? So it's formation of gaseous sodium from solid sodium, all right? Then what? All right, well, what changed here? I'm going to break this chlorine bond, and so I get only one chlorine atom. So formation of chlorine atoms from a chlorine molecule, all right? And then what? Ionization. I need to make ion of my sodium, all right? Gas, or neither of them are ions yet. So what happens? I need to rip off an electron from sodium. All right, what's that called? Ionization energy. Yeah, this is my ionization energy. Now what? I have to make my chlorine become chloride. So notice how ionization energy requires energy. Well, look down here. Chlorine is that electron affinity. So I'm going to clap again. This is when the electron goes whoop, all right, is attracted to that chlorine atom because of electronegativity. And so that whoop, all right, gaining that electron is exothermic. So you're going to come down here. This is your negatives, isn't it? So now look what I have accomplished. I have sodium ion gas, I have chloride ion gas, okay? What can I do now? I can now make sodium chloride. This right here, if you want to write this down, this step number 5 is lattice energy, all right? Step number 5 is lattice energy. While you're at it, why don't you go ahead and label this. Step number 4 is electron affinity. Notice it's negative. Step number 3 is ionization energy. All right. I already referenced number 1 was sublimation, and then this was just breaking that chlorine bond. All right, just breaking bonds. Okay. So anyway, that is how we can get from sodium solid and a half a chlorine gas going down to sodium chloride. We have to go through those 5 steps. All right. So this is what's called the Born-Haber cycle. Haber was also very well known for making ammonia out of hydrogen gas and nitrogen gas, and he got very, very wealthy off of that too. But he worked with Born and came up with this whole idea of this entire cycle here. So guess what? There are values associated with all this stuff. So we know my final result. We know that right here, do you see this step that I'm circling right here? That step we said earlier was at negative 411 kilojoules per mole. So this right here is negative 411. So my net result is a negative exothermic. Okay, it's not always that way, but this time it is. All right, so the first step was sublimation. I told you about that. And the second step was what's called bond energy, which is, I had to multiply by half, so it's half of what you'd look up, which would be 244, which is half of that, it's 122. This ionization energy is that 496, all right? The electron affinity, whoop, it came together, negative 349. And now what is that lattice energy? I don't know. Let's call this X, okay? So what did I do? Well, it's Hess's law, right? Let's add this. I forgot about this. Don't forget about the add about 122. I know it's a little off-center there, but so 108 plus 122 plus 496 minus 349 is what? Use your calculator. What does that equal? Hopefully you got it. It's 377. So 377 plus my lattice energy is equal to what? negative 411. All right, that's using Hess's law, right? So when we're done, we could figure out that Hess's law, I'm sorry, we could figure out the lattice energy is negative 788. Now, I just want to remind you what we can do with Hess's law. Is there anything I can cancel out? Yeah, look at sodium gas and sodium gas. Look at this, sodium ion and sodium ion. Here's a chlorine atom and a chlorine atom. What else? Chloride ion, electron, electron. And so what am I finally have? Here are my reactants, here is my product, and this is what I have right here. So hopefully that kind of brings back some memories. I don't know if they're fond or not, but there should be some kind of memories. And so we're going to do the same thing now with lithium fluoride. Okay, so let's go to the next page. So notice that the series of steps are really the same idea, aren't they? So what is my goal in this problem? It is to solve for the delta H of formation. Like if you could go back and look at the back of the book and take, products minus reactants. That's what we're trying to do here. But watch what we can do once again. We can start looking at this. So going from solid to gas, that's your sublimation, and there's a value for that. Going from lithium gas to lithium ion is ionization energy, and that's 520. Then I have to take this half of fluoride or fluorine, to make one fluorine atom. All right, so I'm going to multiply the bond energy by half and get 77. And then I'm going to take that atom of fluorine, I'm going to gain an electron. Notice it's a negative number, and I'm giving you the lattice energy this time. All right, it's negative 1047. So I'm going to show you something real quick. All right. What kind of things can I start canceling now? Well, I think I can cancel out the here, and I can cancel out this, and I can cancel out, let's see here, F minus gas. Oh, here's this over here. Oh, I have an electron I can cancel out. So now I have lithium solid and a half of fluorine gas. Those are my reactants, and here is my product. All right. So that is, again, what I'm looking for. This is my delta H of reaction. So how am I going to solve for it? Well, folks, just add this all up. What's 161 plus 520 plus 77 minus 328 minus 1047? What do you get? I got negative 617. All right. So use the following data to estimate the heat of formation for magnesium fluoride. It's a little bit different, okay? So here I go, all right? And this is what I'm going to start with. Now let's write out the equations, all right? So write out all equations. So let's go ahead and do this. All right, well, what did we do the first time, all right? We had to have sublimation of magnesium. What does that mean? I need to go from, I'm going to start right here, magnesium solid, and the F2, I'm not going to change anything to the F2. I'm just going to make it go from a solid to a gas. So how much does this arrow go up by? 150 kilojoules per. So I'm going up. It requires 150 kilojoules of energy. Well, what's the next thing I need to do? I need to ionize magnesium. What does it say? The first ionization of magnesium. All right, so what does that mean here? I only strip off one electron from magnesium. So what do you think I have to do next? Strip off the second electron. Wow, that's a lot more energy. Oops, wrong one. A lot more energy, isn't it? It sure is. Why does it take almost double the amount of energy? Because it has a greater effective nuclear charge. Those electrons are going to be held more tightly to the nucleus because now I have more protons than electrons after I strip one off. So it takes much more energy to strip off the second one. All right, now what do we have to do? Well, what comes next? Looks like I have to form just a fluoride from fluorine. All right, not fluoride, just one fluorine atom from fluorine. Now, why don't I multiply it by half? Because look at my formula. It is F2 right here, right? I need both of them. So I don't need to, what was I going to say? I don't need to multiply by half because I need both fluorines, all right? So now I'm at the tippy top. I've done all my endothermic reactions. So I go from F2 to F, and that's a gas too. I'm sorry I didn't stick that in there. So now what? Well, fluorine atom isn't going to do anything. What do I need? I need fluoride ions, all right? So notice I took the electron affinity of fluorine, all right, and I multiplied it by 2 because I have 2 F minuses, all right? So, oops, that is negative, what did I say, about 600 and something, all right? And then what? Let me scroll down a tad more. There we go. I now need to go, here we go, look. I have their ions, magnesium ion in the gas, fluoride ion in their gas, and what's my goal? To make magnesium fluoride. What do I define that as? That's the lattice energy, all right? So now what do? I add, subtract, and what do I get for the heat of formation? That's what this red line is the heat of formation. That is going to be hopefully negative 2088. Okay, so that's where I go from its elements in its natural state to the solid. That's the heat of formation, if you recall. All right, but I had to go from their lattice energy down to that. Okay, that's your Hess's law. Now, what's the so why is the lattice energy of magnesium fluoride about twice as lithium fluoride? That's a great question, all right? What does it say here? Well, magnesium has a charge of a 2+, while lithium has a charge of a 1+. So the charge has much more to do with the difference in lattice energy as the radius, all right? Only small changes in radius versus a whole number difference in charge, all right? So it's almost twice as much, all right? So why is that about 3 times as much as sodium chloride? Go back and look what we said what sodium chloride is. Well, not only do we have a +1 here, all right, but also fluorine is what? Smaller. So between the two of them, magnesium has a charge of +2 and sodium has a -1, all right? But what? Also the fluorine has a smaller radius, okay, making chloride that much, the lattice energy that much more greater, all right? So here, I didn't even look at the fluorines because they're both the same size, but not only do I have a difference in charge of lithium and magnesium, I also have a difference of size between the fluorine and the chlorine, all right? So between the two, remember what I said about being directly related with the charges to the energy and then indirectly related to the size versus the energy. So that's really kind of a big deal there, isn't it?